Category O, Lecture 24, Serre functors. We start with a general theory of Serre functors. Let K be a field. As usual, we denote by star the usual K duality. Let A be a K linear category. Assume that A is Hom finite, which means that the dimension of the K-space of morphisms from any object I to any object J is finite. Definition: a K-linear endofunctor S of A is called a right Serre functor, provided that for all I and j in A, there are isomorphisms between Aij and AJSI dual, which are natural in both I and j. Remark: directly from the definition it follows that A has a right Serre functor if and only if the functor AI blank dual is representable for any object I in A. In case this functor is representative, it must have a form A blank to some object in A, and this object is denoted by S of I. So this then gives us a definition of S. This gives us directly the property that in the case a right Serre functor exists, it is unique up to isomorphism. A right Serre functor is called a Serre functor if it is an equivalence. It is very easy to see from the definitions that any right Serre functor is full and faithful. Therefore, a right Serre functor is a Serre functor if and only if it is dense, or essentially surjective. Observation: if S is a right Serre functor on A, and F from A to A is any equivalence, then F and S commute. It is very easy to check that the conjugation of S by F is a right Serre functor on A, and hence this must be isomorphic to S because of uniqueness of right Serre functors. Serre functors were introduced in the paper by Bondal and Kopranov in 1989 and studied in detail by Reyten and Vandenberg in 2002. A lot of things which will be discussed today are taken from my paper with Katarina, which is called Projective Injective Modules, Serre functors and Symmetric Algebras from 2008. In the setup of finite dimensional algebras, Serre functors are related to Nakayama functor. So let A be a finite dimensional K algebra. Consider the dual bimodule A star. Then the Nakayama functor n on A mod is defined as tensoring over A with this dual bimodule. Directly from the definition, it follows that n induces an equivalence between the category of projective A modules and the category of injective A modules. The Nakayama functor has an alternative description as the functor of homing from blank to A and then taking the K duality star. So to prove this, we note that both functors tensoring with A dual and hom from blank to A dual are right exact by definition. So to prove that they are isomorphic, we need to compare them on projective A modules. So taking the projective generator A of A proj, the image of A under tensoring with A dual is of course A dual. But this is also the image of A under homing into A and then taking the dual. And this isomorphism is an isomorphism in the category of AA bimodules. So this proves the alternative description of the Nakayama functor. The relation between Serre functors and Nakayama functors was established by Happel in the following theorem. If the algebra A has finite global dimension, then the left derived of the Nakayama functor is a Serre functor on the bounded derived category of A. So this was proved in the paper by Happel on the derived category of a finite dimensional algebra from 1987. Let us now discuss the proof. For any pair M and N of A modules, where M is projective, we have the following: that A homomorphisms from N to A star tensored over AM, and then taking the dual, are isomorphic to, in this first step, we rewrite the second argument using the alternative description of the Nakayama functor. And now the second argument becomes hom over K, hom over A from M to A, and then to K. Now we can use the usual hom and tensor adjunction, and we write this as hom over K, and then the first argument will be hom over A from M to A, tensor over A with N, and then we take this hom into K. Now we see here taking the double dual, which we can just erase. So the outcome is hom over A from M to A, tensored over A with N. Since M is a projective A module, we can pull N inside the hom. So this is isomorphic to hom over A from M to A tensor over A with N. And then we can contract the second variable to N. And the most crucial place is here in the middle, where we use that M is a projective module. So we have a natural isomorphism from hom over A N, comma, the Nakayama functor applied to M, dual, and hom over A from M to N. So this isomorphism can now be extended to the whole of dBA, because the left derived of the Nakayama functor is a triangulated functor, and dBA is generated as a triangulated category by projective modules. So this proves that the left derived of N is a right Serre functor, and we will later prove that this functor is in fact an equivalence. Before we go on, let us make a couple of remarks. First of all, the module category A mod usually does not have a Serre functor. As was shown by Van den Berg and Drayton, a triangulated category has a Serre functor if and only if it has Auslander-Drayton triangles. Bondal and Kopranov showed that a Serre functor on a triangulated category is necessarily a triangulated functor. If the algebra A is Gorenstein, which means that the injective cogenerator A dual has finite projective dimension, then the left derived of the Nakayama functor is a Serre functor for the category of bounded complexes of projective A modules. So this is a category of perfect complexes for A. From this it follows that an algebra A is symmetric, and here symmetric means that A is isomorphic to A dual as an AA bimodule. So an algebra A is symmetric if and only if it is Gorenstein, and the identity functor is the Serre functor on the category of perfect complexes for A. Let us now go to category O. Let G be a semi-simple finite-dimensional complex Lie algebra with a fixed triangular decomposition. Consider the principal block O0 of the associated category O and the corresponding bounded derived category dB of O0. Let W be the Weil group. Previously, we have seen the following endofunctors of O0. We have the projective functors θ W, the shuffling functors CW, the co-shuffling functors KW, the twisting functors TW, Joseph's completion functors JW. And we know that the derived versions of shufflings, co-shufflings, twistings, and completions are all self-equivalences of the bounded derived category. So now we can describe the Serre functor on dBO. Recall that category O has finite global dimension, so from the general result of Happel, we have that for any block A of O, the corresponding bounded derived category has a Serre functor, which is given by the derived Nakayama functor. Let us denote the longest element of W, as usual, by W0. So here is a Lie-theoretic description of the Serre functor on dBO0. Theorem due to Katerina Stroppel and myself. The Serre functor on dBO0 is isomorphic to the square of the left derived of the twisting by W0. It is also isomorphic to the square of the left derived of shuffling by W0. Note that the square of W0 is the identity element in the while group. However, it is not the identity element in the braid group. In fact, outside type A1, W0 squared generates the center of the braid group corresponding to W. There is also a geometric description of the Serre functor on dBO0, which can be found in the paper by Belinson, Bezrukavnikov, and Mirkovic from 2004. The aim of today's lecture is to prove this Lie-theoretic description of the Serre functor on dBO0. Let us start with comparing the square of the left derived of TW0 with the square of the left derived of CW0. Claim these two functors are isomorphic. So we will prove this claim in type A, where the proof is very easy. We know that in type A, for any W in W, the composition of LCW0 with theta W is isomorphic to the composition of theta W0 WW0 with LCW0. So the left derived of CW0 commutes with projective functors up to conjugation of the index by W0. From this it follows that the square of the left derived of the W0 shuffling commutes with all projective functors. And we also have seen that the square of the left derived of both twisting and shuffling by W0 maps the dominant projective module delta E to the dominant injective module nabla E. And we also recall that the category of projective objects in O0 is the evaluation of the category of projective functors at this dominant object delta E. Since both functors LTW0 squared and LCW0 squared are defined on projective modules, both commute with projective functors, and both send delta E to nabla E, they must be isomorphic. In order to proceed, we need to recall the double centralizer property and the dominant dimension property. Let A be a finite dimensional algebra and Q a projective injective A module. Recall that A mod has dominant dimension at least 2 with respect to Q if there is an exact sequence, if you can take the projective generator, embed it into a projective injective module, such that the cokernel of this embedding again embeds into a projective injective module in the additive closure of Q. And we have seen that the above property implies the following statements. First of all, the functor hom over A from Q to blank, and this is a functor from A mod to the category of modules over the endomorphism algebra of Q. This functor is full and faithful on projectives. And then we have the double centralizer property that the endomorphism algebra of Q as the module over its endomorphism algebra is Morita equivalent to A. And we also know that category O0 has dominant dimension at least 2 with respect to the antidominant projective injective module PW0. In order to prove the main theorem, we will use the following characterization of Serre functors using dominant dimension and double centralizer property. So this is a theorem due to Katarina and myself. Let A be a finite dimensional algebra of finite global dimension. Assume that both mod A and A mod have dominant dimension at least 2 with respect to a projective injective module, and that the top of each projective injective module is isomorphic to its socle. Let f be a right exact functor of a mod such that the left derived of this functor is an equivalence of the bounded derived category. F maps projective A modules to injective A modules, and F preserves the category of projective injective A modules and is isomorphic to the Nakayama functor when restricted to this category. Then F is isomorphic to the Nakayama functor. In particular, the left derived of F is a Serre functor on DBA. To prove this theorem, let us start with describing that the Nakayama functor actually has all the properties which are described in the second part of this theorem. First of all, we claim that the left derived of the Nakayama functor is a self-equivalence of DBA. To prove this, we consider the adjoint of the Nakayama functor, which is a right derived of hom over A from A star to blank, and we make the following computation. So if we start from the projective generator A, apply the left derived of the Nakayama functor, and then the adjoint functor. Then, since A is a projective module, we can delete the left derived part to get the R hom over A from A star to NA. Then we know that N of A is just A star. And now we are computing hom into an injective A module, so we can delete the right derived part and rewrite A star as hom over K from A to K. Now, using the usual adjunction, we can move over this hom over K from A to the left argument as a tensor product. And of course, tensoring over A with A is the identity. And here now we can remove the double dual to obtain A. So starting from A and applying first the Nakayama functor and then its adjoint, we get A. So this essentially implies that the Nakayama functor and the adjoint are inverses to each other from one side. And similar computation can be done from the other side. And since A generates DBA, it follows that the left derived of the Nakayama functor and its adjoint are mutually inverse equivalences of categories. The fact that the Nakayama functor maps projective modules to injective modules follows directly from the definition. We claim that under our assumptions, the Nakayama functor maps projective injective modules to projective injective modules. To see this, let us compute N of the projective module AE. By definition, using the alternative description of the Nakayama functor, this is hom over A from AE to A dual, which is just the dual of EA. And this is AE because we have assumed that the top and the socle of each projective injective module are isomorphic. So we proceed with our proof of the characterization of Serre functors. And now let us compare the functor f from the formulation of this characterization with the Nakayama functor on injective modules. So the claim is that these two functors are isomorphic when restricted to the category of injective A modules. Proof. So we have assumed that both A and A op have the dominant dimension property with respect to projective injective modules. So this means that the injective cogenerator A star admits a two-step resolution by projective injective modules. Let us choose some isomorphism eta between F and N on the category of projective injective modules. So applying the right exact functors F and N to this presentation of A star, we will get the following diagram where eta q1 and eta q0 are evaluations of eta at the modules q1 and q0 respectively. So here we have the solid square which commutes, and the commutativity of the solid square as usual induces a map which we denote by eta A star from F A star to N A star. And from the phi of lemma, it follows that this map is an isomorphism. So this implies our claim that F and N are isomorphic when restricted to the category of injective A modules. The previous slide can be generalized. If we denote by X the full subcategory of A mod, which consists of all modules having a two-step presentation by projective injective modules, then, similarly to the previous slide, both F and N restrict to endofunctors of X, and these restrictions are isomorphic. Clearly, the functor N is invertible as an endofunctor on projective injective modules. Consequently, the restrictions to X of both F and N are invertible as endofunctors of X. So now we can prove our characterization of Serre functors. What we need to prove is that the restrictions of F and N to projective A modules are isomorphic. So since the Serre functor commutes with any autoequivalence, it must commute with the left-derived of F, since this left-derived functor is an equivalence. Taking the zero homology in this isomorphism, we get that the restrictions of NF and Fn to projective A modules are isomorphic as functors. Since both F and N send projective A modules to injective A modules and are isomorphic when restricted to injective A modules, we obtain that the restrictions of NF, the first guy, and NN, so I change F to N here, these two restrictions to A proj are isomorphic. Since the Nakayama functor is invertible on X, it follows that the restrictions of F and N to A proj are isomorphic, because in this isomorphism we can multiply with an inverse on the left, giving us our claim. Now let's go back to the main theorem. So we want to prove that the square of the left derived of the twisting by W0 is a Serre functor on O0. And of course we want to use our characterization of Serre functors. We know that O0 has dominant dimension at least 2 with respect to projective injective modules. And we know that the algebra of O0 is isomorphic to its opposite due to existence of the simple preserving duality star. So we have this dominant dimension property both for A and for A op. We also know that O0 has unique indecomposable projective injective module, namely PW0, and that this module is self-dual, in particular has isomorphic top and socle. Finally, given a reduced expression of W0, we know that the square of the left derived of TW0 is isomorphic to the composition of left derives of elementary twisting functors following the square of this reduced expression. Therefore, we will try to apply our characterization of Serre functors to the functor f defined as TW0 squared. Okay, so let us prove our main theorem. Well, we already know that the left derived of TW0 squared is an equivalence. So let's check that TW0 square maps projectives to injectives. We know that TW0 squared maps delta E to nabla E, and we know that it commutes with projective functors. Applying projective functors to delta E, we can get all projectives, and since projective functors preserve both projective objects and injective objects, we get the claim. Next, let us prove that TW0 square maps the projective injective module PW0 to itself. Indeed, TW0 square applied to PW0 is isomorphic to the following, so we can rewrite PW0 as delta W0 applied to delta E. Now we can compute delta W0 and TW0 squared. The application of TW0 squared to delta E gives nabla E, and applying theta w0 to nabla E gives iw0, which is isomorphic to pw0. Next, we claim that the restriction of tw0 squared to the additive closure of pw0 is isomorphic to the identity functor. Well, we know that twisting functors commute with the action of the center of the universal enveloping algebra, and that the latter center surjects onto the endomorphism algebra of pw0 by Zergel's endomorphism and Satz. This implies the claim. Hence, to complete the proof of the main theorem, we need to prove that the restriction of the Nakayama functor to the additive closure of pw0 is isomorphic to the identity functor. So let us now discuss the restriction of the Nakayama functor to pw0. We know that the endomorphism algebra of pw0 is the coinvariant algebra C of W. And we know that this algebra C is symmetric, for example, because it is commutative and self-injective. Therefore, the Serre functor on the category of perfect complexes for C exists and is isomorphic to the identity functor. On the other hand, the restriction of the Nakayama functor to the additive closure of pw0 induces, of course, a Serre functor on this category of perfect complexes. And consequently, the restriction of the Nakayama functor to add pw0 is isomorphic to the identity functor. And this now completes the proof of the main theorem. Our main theorem can be used to describe Serre functors for S subcategories in O. Let P be a parabolic subalgebra of G containing the Borel subalgebra H plus N plus. Let WP be the corresponding parabolic subgroup of W. Recall that a projective PW is called WP admissible if W is the longest representative in the coset of W modulo WP, where WP acts on the left. And then we have the corresponding S subcategory S0P in O0, which consists of all modules which have a two-step presentation by WP admissible projectives. From the main theorem, we immediately obtain that the square of the left derived of the twisting functor by W0 restricts to a Serre functor on the category of perfect complexes for the S subcategory S0P. Let us now make a couple of remarks. Note that the Serre functor on O0 is the square of the Ringel duality functor. Indeed, the twisting by W0 is a Ringel duality functor which sends projective modules to tilting modules. One can use the main theorem to give a similar description of the Serre functor on singular integral blocks of category O, also in terms of twisting functors, but no longer shuffling functors. The Serre functor on the boundary derived category of O0 satisfies the property that all different integral powers of this functor are not isomorphic. This is seen in the easiest way when we apply the Serre functor to the simple object LE. So the case power of S applied to LE gives us LE, which is shifted in the homological position by k times 2 lengths of W0. The Serre functor on DBO is not isomorphic to any shift functor of the boundary derived category because of the previous remark and the property is that the image under the Serre functor of the projective injective module W0 is this projective injective module W0 without any homological shifts. And finally, the twisting functor TW0 is the identity when restricted to the category of injective objects in O0. However, the Serre functor, which is the left derived of this twisting functor, is not the identity because it is not acyclic on injective objects. So let us do the following SL2 example. In the case of SL2, the Weil group consists of the elements E, and S. And we have 5 indecomposable objects in O0, the projectives at E and S, the injective IE, and then the simples LE and LS. The images of the projective objects under the Serre functor are very easy to compute. So PE is sent to IE and PS is sent to PS. So here are the projective resolutions of the simple objects and their images under the Serre functor. So the simple object LS has a two-step resolution, so it's covered by PS and the kernel is PE. When we apply the Serre functor, so PS goes to PS, it's also shifted in degree, and PE becomes IE. So we get a complex with two new homology places of the form LE. So the simple LE has a three-step resolution, so PE, PS, PE, and when we apply the Serre functor, so PE will go to IE, PS to PS, and PE to IE. And we see that the homology, which was originally in the homological position 0, now moves to the homological position -2. And it also changes, so it moves 2 steps up in the gradient. And here is the projective resolution of IE and its image under the Serre functor. So IE is covered by PS, the kernel is covered by PS, and the kernel of this is covered by PE. When we apply the Serre functor, both PS remain PS, shifted in degree, and PE becomes IE. So our homology IE in position 0 is preserved, and then we get the homology LE and LE in homological positions -1 and -2. One can give an alternative description of the Nakayama functor on O0 using Harish-Chandra bimodules. So let H denote the category of Harish-Chandra GG bimodules, and let asterisk in the circle denote the restricted duality on H. So we don't dualize the whole space of the bimodule, but we dualize the isotypic component of finite-dimensional diagonal summands of this bimodule. So we have the BG equivalence between the block O0 and the category H001 infinity, given by taking the ad finite homomorphisms from delta E to blank. This goes from O to Harish-Chandra bimodules, and the functor back is just tensoring with a dominant Verma module over U of G. Theorem, which is due to Vanessa Mimitz and myself, that the functor L blank delta E, and then taking the restricted dual, followed by tensoring over U of G with delta E, is isomorphic to the Nakayama functor on O0. So one of the ways to prove this is to do a lot of adjunctions. Alternatively, one can show that this functor commutes with projective functors, and then it is easy to check that it sends the dominant Verma module delta E to the dominant injective module nabla E, and hence it must be isomorphic to TW0 squared. And this form of the Nakayama functor can be compared with the alternative description of the Nakayama functor. So this L blank delta E, and then taking the restricted dual, should remind you on home over A blank A, and then taking the dual. So this theorem is proved in my paper with Vanessa, which is called Serre functors for Lie algebras and superalgebras from 2012. Let us finish with a couple of questions for PhD students. Question number 1. Give full details of the proof that for any Mn in A mod with M projective, there is an isomorphism home over A from M to A, tensor over An, and home over A from M to N. Question number 2. Let F be a right exactand functor of A mod, which sends projectives to projectives and is invertible on A approach. Prove that F is an equivalence. Question 3. Check with all details that the square of the left derivative of twisting by W0 restricts to a Serre functor on the category of perfect complexes for S0P. Question 4. Describe Serre functors for integral singular blocks of category O in terms of twisting functors. And question number 5. Prove that the square of twisting by W0 is isomorphic to the cube of twisting by W0, while the square of the shuffling by W0 is not isomorphic to the cube of the shuffling by W0. Everything as endofunctors of O0. Thank you very much and see you next time.